The Transportation Safety Board of Canada has released the preliminary report on the Endeavour Air Flight 4819 that crashed in Toronto back on 17 February. It's Friday the 21st of March. My name's Juan Brown. You're watching the BLANCOLIRIO channel. Let's get into it. Now that we have the data for the final few seconds of the flight, we can determine what the crew did or did not do, because whatever happened to this crew happened in the final 14 seconds of the flight from an altitude of about 175 feet above the ground. Prior to that point, everything on the approach was stabilized and there was nothing wrong with the airplane. The crew was landing on Toronto's runway 23, where the runway had been recently plowed to a width of 160 feet. Now the total runway width is 200 feet. So the runway is appearing a little narrower than normal. The winds are blowing out of the west 270 degrees, anywhere from 20 knots to 28 knots, with gusts from 32 knots up to 35 knots. Looking at the crosswind for runway 23, wind direction out of 270 degrees, 28 knots, not counting the gust, gives you a crosswind component of 18 knots. Now the magnetic heading for runway 23 is actually 237, so if we cut this for 240 degrees, that gives you a crosswind component, knocks it down to 14 knots. But if we add the gust component of 35 knots, that crosswind component bumps up somewhere between 17.5 knots and 22.5 knots. And the visibility is 6 statute miles in blowing snow, and that snow is blowing across the runway. I bring all this up because one of the things missing in this report are the specific crosswind limits for this aircraft in these conditions and the crosswind limits for the crew based on their experience in these conditions. So far, the TSB has found nothing wrong with the aircraft mechanically that could have precluded a normal landing. As I've said before on this program, gusts can kill you, and in the airline industry, we help mitigate this risk by adding a gust additive to our final approach speed in gusty conditions. But what I find surprising in the Endeavour aircraft, or in the CRJ aircraft at Endeavour, is they only add a maximum of 10 knots for this gust additive. Normally, with the larger jets that we fly with the rest of the airlines, we normally add up to 20 knots for a gust additive. So each flight, a reference speed is calculated based on our configuration and our weight and where we're going into land, and the approach speed is set at VREF plus 5 knots. But in gusty wind conditions, you want to give you an extra margin of safety for cutting through those gusty wind conditions, and that's why we add this gust additive. Because as we're about to find out, the gusts can knock you around faster than the pilot can react. And here's another thing I find interesting as your procedure here at Endeavour. You still set your VREF plus 5 bug speed, but then you fly the 10 knot faster speed. Normally, the policy I'm used to is that you go ahead and set your gust factor in your bug speed setting, especially on an aircraft with auto throttles. Now, I know the CRJ does not have auto throttles, but on aircraft with auto throttles, you need to set that gust factor in your VREF so the auto throttles know what speed to key off of or to maintain. So is this normal policy at Endeavour where you just set your REF plus 5 and then fly your gust additive on top of that? Or do you set your bug speed to your gust additive? So let's pick this up at 14:12:01. We're about 43 seconds from impact. Everything's ops normal up to this point. They're coming through 500 feet. Everything's stabilized at 150 knots and a ground speed of 121 knots, indicating a substantial headwind. And the thrust is set at 64% N1. So a good stabilized approach with the power up. N1 is apparently your primary engine indicator on the CRJ. And they're descending at a nominal 720 feet per minute with the localizer glide slope centered. 5 seconds later, the autopilot is disconnected. Now remember, the gust additive speed that they want to fly is 149 knots, right there next to 150 knots. About 26 seconds later, the aircraft's descending through 175 feet AGL. Indicated airspeed is down to 144 knots, okay, a little bit slow, and the ground speed's 121, still that headwind, and the descent rate 672 feet per minute, and thrust remaining up there at 64% N1. At 14:12:30, now we're just within 14 seconds of impact. The aircraft descending through just 153 feet above the ground. The indicated airspeed increases to 154 knots, whereas the ground speed did not change appreciably, consistent with a performance increasing wind gust. And here's the hazard with a performance increasing wind gust. All of a sudden you get a big headwind coming at you. The aircraft can't react to it fast enough. The airspeed picks up, and so the natural pilot reaction is to come back on the power. That's going to set you up for a big sinker. The pilot flying, remember the pilot flying is the pilot in the right seat, and the captain is in the left seat, the FO is in the right seat, so the FO is doing the flying. The pilot flying pulled back the thrust levers, and as a result, over the following 5 seconds, N1 decreased from 64 down to 43%, where it remained until touchdown. And there's the big problem. 43% is darn near at idle RPM. The airspeed began to decrease. At 14:12:40, just 3.6 seconds before touchdown, when the aircraft was at a height of just 50 feet AGL with an indicated airspeed of 145, remember we wanted to maintain closer to 150 knots. The ground speed was 112 knots. The rate of descent had increased to 1,114 feet per minute. Pitch and power. You need to arrest that descent rate with the power. 1 second later, just 2.6 seconds before touchdown, the EJIPWIS sync rate sounds. That's an automatic sync rate warning from the automation in the aircraft. The aircraft's indicated airspeed is 136 knots. Again, we need it to be up closer to 150 knots. Why? Because that power is still way back there. Its ground speed is 111 knots, and the rate of descent remains at 1,100 feet per minute. The bank angle increases to 4.7 degrees to the right, and the engine thrust remains at 43% N1, just a little bit above idle. Just 1.6 seconds prior to touchdown, the aircraft's indicated airspeed rolls down to 136 knots. Remember, we want 149 or 150 knots, and its ground speed is 111 knots. The aircraft was beginning to drop below the glide slope, but still on a visual segment of the approach and tracking the runway centerline. But the rate of descent had increased to 1,072 feet per minute, and the right bank angle was 5.9 degrees to the right. At 1 second prior to touchdown, the indicated airspeed 134 knots, ground speed 111, bank angle increases to 7.1 degrees to the right, and the pitch was only 1 degree nose up. So there's no effort to flare here, just as we saw in the initial reports. The aircraft is just being driven straight into the runway, and the rate of descent is recorded at 1,110 feet per minute. Remember, your normal rate of descent at this point would be something on the order of 600 feet per minute or less. Hopefully, right as you flare, you want to bring that down to nearly zero. At 14:12:43.6, that's when the right main contacted the runway at 7.5 degrees of bank and 1 degree nose up in a 3G impact. That means if your aircraft, at the time, this aircraft weighed 73,000 pounds. 73,000 times 3 is a 219,000 pound force imparted on the right main landing gear at 1,098 feet per minute. So the first thing that fails as a result of this hard landing is the right main landing gear side stays shown here. The side stays are what keep the gear in the down and locked position. With the side stays failed, the gear simply folds up. It retracts. That puts that entire 3G load now onto the right wing. And the right wing fails, and here's a picture of the rear spar. You see this row of rivets right here? This is how these things fail in shear load. This row of rivets is just like a bit of note paper on a spiral bound book, where the spirals represent the rivets and they begin to fail just like that. The gear folds, the wing fails, the fuel leaks or explodes out of the right wing as that fuel tank is now exposed, and the lift on the left wing rolls the aircraft inverted. A successful evacuation was done with the aircraft inverted, with folks leaving out of the one right door and the aft right overwing exit, the forward overwing exit being drenched in fuel. The pilots were unable to leave the cockpit as the cockpit door was jammed shut and there was a flight attendant seat also preventing the door from opening. So the pilots had to use the emergency escape hatch located on top of the cockpit area, but they were, of course, now that's nearly on the ground, and with the help of a passenger, they were able to squeeze out of here. There was also a deadheading pilot and flight attendant on board the flight that was able to assist in the evacuation. So when investigators get done with their final report, they'll have some data drawn out that's going to look something like this. With this performance increasing headwind shear, here's your normal glide path, desirable glide path to the runway, and you get this increasing headwind shear. The airspeed begins to increase, you generate more lift, and you begin to climb slightly above glide path, and so the pilot reacts by reducing the power. Now normally, right about here, you should either A, go around, or B, understand that there's going to be a big payoff or sinker at the end of this thing, and you got to be ready to accept a longer landing if you've decided not to go around. Because if you keep this power back like this pilot did, you're going to get into the sinker phase of it and come up short. Another thing I want to point out that I mentioned at the beginning of the video was that the runway was plowed to 160-foot width, where the normal runway width is 200 feet. So that's the narrow runway illusion. With the runway more narrower than usual, you are going to think that you are higher than normal, and you are going to delay your flare as a result and plow it into the runway on a narrow runway. And the other factor that should hopefully come out in pilot interviews is, what about this blowing snow across the runway? Did that bedazzle you or confuse you, or was that a factor in your decision to flare the aircraft or land the aircraft? Was that a problem? Now, dealing with all these different factors that I've talked about in the final 14 seconds of the flight really comes down to experience. Having the experience to deal with these sort of conditions, the experience and the training. And I can tell right here at this report that this pairing, it was not a great pairing, pilot pairing to begin with. Now, the captain's been working for Endeavor since 2007, has 3,570 hours total time, and only 764 hours on the type. It doesn't say how long he's been on the aircraft, but it sounds like his main job is working in the simulator, because he's only got 3.5 hours of actual flying experience in the last 30 days. So that's not a lot of total flying time, having been hired by Endeavor all the way back since 2007. Most of his experience, it sounds like, is in the simulator. Now, as was erroneously reported out there on social media about these pilots, there is no mention of these pilots having ever busted any check rides or had any problems in their prior training, and that forced Delta Airlines to make that statement, to have to come out and say that. Now, the first officer had been with Endeavor just since January 2024, and she already had 418 hours in the aircraft type, compared to the captain's 764 hours in type, having been worked there since 2007. And the first officer in the last 30 days had already done 3 round trips to Toronto and had 56 hours in the last 30 days. So she's the more experienced of the crew for landing in these conditions at Toronto. But she's working with a restricted ATP with only 1,422 hours total time, and we explained what a restricted ATP means in the previous update on this crash. So the TSB is going to look at all these different factors as they continue to evaluate this accident, including pilot training. But it's this fundamental lack of experience in the entire industry that's beginning to cause these sorts of problems. And if these pilots never flunked any sort of training programs, if they were able to pass their training programs just fine, what sort of training are we giving our new pilots? And here's where I agree with Rod Machado, longtime professional instructor pilot, been around long before the internet was even invented. Somewhere along the way, in our rush to backfill the sudden pilot shortage, we've lost our fundamental stick and rudder flying and training skills. As Rod says, we now emphasize this higher order of flight training that gets kids into doing very complex tasks right out of the gate and quickly glossing over the basic stick and rudder skills that have been vital to aviation safety since the dawn of aviation. Thank you so much for your support of this channel, especially the folks over on Patreon that make this content possible. See you here.